Yeah. So this morning I want to introduce what we refer to as integration. Sometimes you hear the term anti-differentiation, right? And just like how you speak of derivatives, you hear of anti-derivative. I think even in Guyana you say anti-derivative. Sounds like some relative of your father or mother. Yeah. So basically the process of integration is the opposite of differentiation, right? It's piecing together, as the term suggests, integrate. You're piecing together, you're putting back together what possibly could have been the original function that you differentiated. Right? So they have an example on the slide here. When you differentiate a function like x squared, you get 2x. So one would think that when you integrate 2x, you get x squared, right? The heading there is telling you something called indefinite integration. And the reason why is that the derivative of x squared is said to be 2x here. But you would know that if there was a constant attached to x squared, maybe you got x squared plus 1, x squared minus 1, x squared plus 5, x squared minus 5, they will all differentiate to give you 2x. And therefore, when you get a function like 2x and you have to integrate it, you're never certain whether the function was x squared or x squared plus something else. And therefore, you will see very often, and we're going to touch on that on this next slide here, right? When you integrate, and they're giving you two examples here, that the function could possibly have been x squared plus 1, it could have been x squared minus 7, and they will both differentiate to give you 2x. And therefore, when you integrate 2x, you are not certain of what the constant was, and therefore you attach, notice the k here. My pen isn't picking up. Oh, sorry about that. Yeah. Yeah, you notice a k at the end here? All of you are seeing when I indicate here?
Yes, sir.
Yes, sir.
So we attach a k there, which we refer to as a constant of integration. There's a reason why they call it an arbitrary constant, right? Let me give you a little explanation of that. I'm not trying to explain every single word on the screen, but let me just say why they call it arbitrary. Because you have, all right, you have, let's say you put it this way. You have dy, let me write it up here, dy dx equal to 2x, right? 2x, good. So when you cross multiply, you get dy equal to 2x dx, right? So you integrate both sides, right? And this is the integral sign here. Is the integral sign. And that sign is like an elongated S, because if you get into the where they came up with this idea of integration from, it involved the summation of areas, right? And that's why this sign, this integral sign, is like an elongated S, right? For summation. And we talk a little about it when we apply it to area, maybe in another day, right? Good. So when you integrate this side, you're integrating like it's like as though there's a 1 here. You're integrating 1 with respect to y, so you get y and you're supposed to get a k, right? So I've called that k with a subscript 1. And when you integrate 2x, you get x squared plus another k, right? So I'll name that k subscript 2. Now you can't have all these constants all over the place, it makes the function look too cumbersome and complex. And therefore you say, man, let's write it like this. Y equal x squared plus k, and a big K, no subscript. And we say, man, this is an arbitrary constant, meaning, the teachers in the class would know when they have wage disputes and the union fighting for 20%, and the government said, you only give me all 5, and so they go to arbitration. And the person they go to, is somebody who is not on the side of the government or on the side of the union, right? He's an arbitrator. And he would not normally negotiate, well, let me find a compromise, somewhere between 5 and 20. Right? And usually, I don't know how they just come to a compromise, 5 and 20, and they just come to like 6% and 8%. I don't know. What kind of arbitration is that? Anyways, yeah, so our constant here, we can say it's arbitrary, meaning it doesn't belong to any one side, right? But we put it here, So it's an arbitrary constant. It could have been over by the y, could have been over where the x squared is, but we put it, because we're used to writing functions like that. Y equal to something plus something, So we're putting it where the x is, right? So it doesn't really belong to just one side. It can go on either side. That's why they call it an arbitrary constant. Good. So, and of course, that's why we call it indefinite integration, because we are not certain what k is. We don't know what k is, right? We need more information. And there are some problems where we're going to find ways of either eliminating k or finding the value of k, right? And you'll hear about those if you do some further studies in calculus and so. We will touch a little bit when we talk about areas, right? You'll see that the k is eliminated, but then there are other situations where you have what you call initial value problems, where maybe some initial value conditions are given, and they'll tell you, well, when x is this, y is that, and therefore you can put those numbers in and find out what k is, right? So we'll come to that a little later. Good. So what we want to do now is we want to find some techniques that will help us to piece together the original function fx, right? So here, and again, as I told you, this is a very introductory course, you're just scratching the surface of calculus here. We did quite a number of functions when we were dealing with differentiation, and I explained to you that is, we haven't touched, much there, right? I mentioned a few that we aren't even going to deal with. Same thing with integration. Integration, as a matter of fact, you might have there's that whole course that the teachers will do, calculus 2. It's largely integration. That course really delves into calculus, right? And in particular, integration. And it will deal with a number of techniques that you can use to integrate some very complex functions. But our intention here, is just to introduce you to some basic techniques to integrate some functions that you might meet up with, So we started a very simple one. Like this is like a power function, So x to some power. And that wasn't very difficult to differentiate, if you remember. We took the n, we multiplied the coefficient 1 in front, and then we reduced the power of the n by, we reduced the power by 1. Remember, the integration is the very opposite now, right? So now we're going to add 1 to the power, right? See up here? We're going to add 1 to the power, and then we're going to divide the coefficient in front, which is 1, by that new power that you get, right? And never forget this plus k at the end, right? Always remember your constant, as I'll trick you now. I will normally write when I give you a problem to do, I say, look, integrate this, and I have A, B, C, D, and you have the right answer without the k, right? And then you when you see it, oh, quickly you tick it, that's the answer. But then you forget the key at the end, right? There'll be one that has the key. Keep that in mind. Yeah. So this is very simple, right? You have some examples here. I have some examples. So we have to integrate this one, x to the 7. Add 1 to the 7, you get 8. Divide the 1 in front here by the 7. Sorry, by the 8, and you get 1/8. Right? If the power is negative, no need to worry. You do the same thing. You do the same thing. Add 1 to the power, becomes -3. You divide the 1 in front here, the 1 in front here, by -3. You have -1/3. And don't forget, you notice key. Right? Your constant of integration. Think you're getting that? Are you following?
Yes, sir.
Yes, sir.
Simple, right? Well, we always start off simple. You know? Clear this one, yeah. And of course, you remember when you differentiated let's say something like 2x, you usually drop out the x, isn't that so? Right? Well, the integral of a constant, you just add on the x, right? It's a power rule, really. It's just a variation of it. Right? You want to think of c as cx to the 0. It's like you add 1 there and divide by the 1, so you'll get cx, right? Plus, of course, your key. Follow that? Do you follow?
No, sir. Where we get the key from?
Who asking that, JC? You just come to this class. Just come in like. Remember, anything you integrate, I was explaining earlier. Let me go back that explanation. Anything you integrating, right? Okay. So you're integrating, so dy dx. Let me use it. Equal to c, right? Equal to c. When you take over this variable over, you get dy, right? And you get c dx. So I'm integrating this side, I'm integrating this side. I was explaining when you integrate 1, there's a 1 here, even though we don't write it, with respect to y, you get y plus k, because I'm saying that I don't know, nobody knows if there was a constant here, right? Maybe there was a constant 1, there was -5, we don't know, right?
Oh, okay, sir.
Over
Yeah.
here, right? You get cx plus another k, because we don't know if there was a constant there, right?
Yes, sir. Thanks.
Therefore, what we do, we merge these two constants, and we say, man, let it be an arbitrary constant. Put it there at the end, right? That's where we got that constant from. Good. So, yeah. And we kind of, all the rules we had before, we just merge them into one now. So we want to integrate something like this, right? Which is like 2x squared, 3x cubed, 5x to the 10 power, that sort of thing. If there's a number other than 1 in front. This is not a new rule. This textbook that I borrowed these examples and so from, they're catering for a very slow learner. And you're really introducing things slowly. But with this rule that you see here, you don't have to worry about nothing else that came before. Right? It captures all of it. Because all you got to think about, if you see something, let's say x to the 5th power, the coefficient in front, c, is 1, right? So this rule kind of generalizes all that we covered so far, right? So all you do, you add 1 to the power, as you see here, and then you divide the constant in front by that new power. And then don't forget this thing at the end here. Right? Sometimes people, I would do it from time to time to kind of see if you really understand what you're doing and so. And there are times when maybe when you differentiate here, you have some negative something, So let's say you have negative 4x squared plus k. Now, this doesn't look good. So I might very well write this k minus 4. The pen skipping today. One day it's blotting and one day it's skipping. Yeah. So I'll write it like this. It looks nicer that way, not so? Doesn't it?
Yes, sir.
Remember, it's even time about nice and so right. Good. So let's go on to some more, well, not more complex, but some more techniques that deal with these very simple functions, right? So maybe you have a polynomial or so, right? Or not necessarily a polynomial, but this isn't. You have a string of terms connected with plus or minus sign. Well, just like when you differentiated, what you did, you differentiated each individual term, right? Well, when it comes to integration, same rules apply. Same rules apply, right? You integrate each term in term, right? I know there's a step here where I write all of this, but just to save yourself all of this writing and all of these signs and so, some people just watch this and go straight to the answer, right? But this is just to illustrate how you're going about integrating a string of terms that are connected, with a plus or a minus sign. You simply integrate each term with respect, well, in this case, we're integrating with respect to x, right? You follow so far?
Yes, sir.
Not hard, right? Not hard so far. Good. Good. So let's go to now integrating what we call the function of a function story, right? Function of a function, right? So you'll remember when we were differentiating, we normally take the power on top, we multiply in front, right? You multiply the number in front here. You reduce the power, then you multiply by the derivative of the bracket, right? Good. So notice what they're telling us to do then. Very opposite. Look here. Oh, not here. No. Sorry. Maybe the next slide will do it. Yeah, here it is. Here's the formula. So you're doing the very opposite now. You're adding 1 to the power, right? and you are dividing in front here. Well, in this case, it's 1. But if there's another number like 2, 3, 5, 10, whatever it is, you put it here. And you divide by n plus 1 times the derivative of the bracket. Now you are differentiating. You are multiplying by the power, and you are further multiplying by the derivative of the bracket. Notice now we are not multiplying, we are dividing. We're dividing by the n plus 1, the new power, times the derivative of the bracket. Notice you never trouble the bracket. You never trouble the bracket, right? And I just want to put an extra condition here and tell you, this formula is only when you have here, when you have a linear function inside the bracket. It does not work, and we'll have to find other techniques to integrate functions where there's a nonlinear. I hope you all by now you all know what I mean. Ax plus b is like y equal mx plus c, mx plus c, right? That's a linear form it has there. If you have ax squared plus b, no, that's not linear, right? That's not a quadratic, right? It's a nonlinear, it's a curve. Or you have ax squared plus bx, again, yeah, that's nonlinear. That this formula wouldn't work, right? Keep that in mind. And this is what you simply do. Look at an example here, right? So you have 3x minus 8 to the 6. Add 1 to the 6, you get 7, right? Never trouble the bracket. Don't trouble the bracket. Write back the bracket. And you divide the coefficient in front here. In this case, it's 1. It doesn't have to be 1. It can be any number. 5, 10, negative 1, half, all kind of number, right? You divide that number by the new power 7 times the derivative of inside here. And by now, you're supposed to watch in here and tell the derivative, right? It's 3. And that's it. Same thing happens here. Look here. Right? Add 1 to the power 9, you get 10. Put back the bracket. Oh, and I'm forgetting the key at the end, right? That's a given. I'm not going to even talk about that. If you don't remember that by now, you're in trouble. So you add 1 to the power, get 10. So you're dividing the number in front here. In this case, I notice they have 1 again. The author should have had maybe, some other number there. And you're dividing that number by the new power times the derivative of the bracket. Notice, in this case, it's minus 5, right? And so on. You see, you don't get scared by the fraction, same thing you do, right? Add 1 to the power, put back the bracket. You're dividing the coefficient in front here, which happens to be 1 again, right? Can be any number, I said it before. And you divide by the new power 8 times the derivative of the bracket, which is in this case minus 1/3. And you stick on your key, your arbitrary constant at the end there, right? Follow so far? So it's a little more complicated. Fortunate for you, you're going to have an open book test. So you're going to write down all the formulas in the world, right? And you have them right in front of you. And I hope you still don't fail the test, even though you have all the formulas in front of you. Good. You're following this one? Can you follow this formula?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. And okay, so we go over to some trigonometric functions, right? And we remember them. The derivative of sine x gave you cos x. So if you were to integrate cos x, you will get back sine x, right? And don't forget your key, right? When you differentiated cos x, you got minus sine x, right? So if you integrate sine x, you will get minus cos x, right? I'll try not to, go much beyond sign and cos when it comes to integration, you know. Especially with the bio people who you haven't done much trigonometry and your appreciation for all the other functions, um, you know, not so, you don't have much knowledge about them, right? And their uses and so. Of course, there's a, maybe in the notes, there's a fuller list, right? There's a fuller list than these two, right? Sec x, tan x, cot x, and so on, right? Those, good. But what about now if you have like cos of a whole function in here, like a linear function, you know, watch here. You have a whole function in there, and mind you, it has to be linear, right? If it's non-linear, this formula doesn't work. Well, you remember if you were to differentiate this, what would you have done? You differentiate the cos, you get sine, right? You have minus sine, sorry. And you normally divide what is in front by the derivative of the bracket, but you're doing the opposite. You integrate in cos, so you get sine. Never trouble the bracket. Stick in your key here. However, in front here, you have to divide the coefficient. It was 1 in this case, 1, but it can be 2, 5, minus 2, all kinds of numbers. That coefficient divided by the derivative of the bracket, which is in this case e. Right? So you integrate cos, you get sine. Write back the bracket. Never trouble what's in the bracket. Stick in a k there. Once you're dealing with indefinite integration, put a k at the end. And then what comes in front here is basically the coefficient in front here divided by the derivative of the bracket, which is in this case e. So it's 1 over e. Follow that one?
Yes,
So
sir.
this, yeah, you switch over a little now to the exponential functions. And well, this is a no-brainer, right? If you differentiate e to the x, you got e to the x, right? Luan is with us. And when we integrate e to the x, we got to get e to the x plus k, right? So this one, there's nothing to do really. And a little further, if you have a constant in front, well, the integral is still the same thing, right? Don't forget your arbitrary constant at the end. Now, what about if you have a whole function in the power, right? You have ax plus b. Oh, by the way, this formula works only if there's a linear function in that power. If there is maybe a quadratic, you know, a non-linear function up there, this formula does not work, right? As a matter of fact, for the maths people, I just want to highlight this here, that the integral of e to the x squared is still one of those unsolved, you know, situations we have, right? And notice that's a nonlinear power you have there, right? So this formula doesn't work when there's a nonlinear function in the power there, right? It only works when there's a linear one there. So again, you write back the exact thing, stick in your key, but in front, you divide whatever number is in front here by the derivative of what's in the power here, right? In this case, it's 1, but it doesn't have to be 1. It can be 2, 5, minus 1, all kinds of numbers, right? But in this case, it's 1. And you're dividing by the derivative of up here, which you see now is a, sorry. You have 1 over a. times the same function you had before, plus k. And they give you some examples here, right? In this case, the number in front of you was 1. So 1 over the derivative of 3x is 3. Write back the function plus k. This one is nice because there's a number 2 in front, not 1. So you put 2, right? You could have written divided by minus 5, right? Dividing by minus 5 is the same as multiplying by minus 1/5, right? Kind of put it a little funny here. Yeah. So you are dividing by the derivative of up there. Follow this one?
Yes, sir.
Okay. Right. And mind you, every one of these is basically a formula you have, right? Basically a formula. Life has become easy for the modern student. Ain't got to hurt the hell at all. Give you all the formula, give you, we tell you open all the textbook and all the notes. You have the internet, everything at your disposal. And yet people, I don't know. All we got to do now is say, here, you can write A on your profile. You got to do nothing. You do on Facebook only and play video games and you write A on your profile. That's the last thing to be done. By then I'll jack up the fees to maybe $1 million a year. Okay. So here it is. You have an took this from an old textbook. That's why you see all this lying. So yeah. When I was a kid, I remember when I was analyzing this thing, I want to know what this guy is doing, Oh, by the way, the writer of this book is 2 women. Yeah. I was a kid and I wanted to figure out what was going on. So you see I'm analyzing it there. I tried to erase, but it didn't come off completely. So here we have a situation. You want to integrate a to the x. And we don't really have a method really, right? So a direct method that is. So what you actually do, you convert, if you notice they're saying, look, let A, because we know how to integrate anything with E inside, right? E to some power. We know how to do that. So what we're trying to do here, we're converting A to the x to something with E as the base, right? E to the Z. And here we evaluate Z by taking the length of both sides, right? And therefore, Z becomes X ln A. So in other words, A to the X can be written as E X ln A. So now we have here something that we can integrate, right? So we came up with the idea that the integral of A to the X is the same as the integral of E to the X ln A, which we just had a formula just now to integrate something that involved E to some linear power, right? X ln A is a linear power, right? So it's equal to, you write back the same thing. Don't forget your K at the end. But in front here, the one that was here, you divide that by the derivative of up here, which happens to be ln E, right? And that's where they got this formula from. Right? So we convert A to the X to something involving E as the base, and then we integrate. Right? You probably remember that from algebra because it involves what we call change of base. Right? You remember this formula, change of base formula? Yeah. But of course, if you can't remember all that, at least remember the formula. And here are some, examples. And then you remember this one. The derivative of, if you remember, the derivative of ln x was 1 over x. Y'all remember that from differentiation? where we use the that Leibniz notation, and where we got dx, dy, and then we interchange the input and so on. I don't know if you remember that video. So when we differentiated ln x, we had 1 over x. Therefore, when you oh, by the way, before you go to that, you see, if we try the power rule, if you think of 1 over x as x to the minus 1, look at what happens. If you were to add 1 here and divide by minus 1 plus 1, look at what happens. You get x to the 0 over 0. See? And therefore, this wouldn't work. This wouldn't work, as you have a division by 0, right? Which is an undefined operation in mathematics. So that power rule really can't work. But we also remember that the derivative of ln x was 1 over x. Therefore, the integral of 1 over x will be, notice we have ln of the modulus of x and not just x, right? This is to ensure that, remember, you can't have the ln of a negative number, right? So we have to ensure that x is positive, right? Or whatever x is, when you, whatever it works out to be, you use the positive of it, right? And then you put a k at the end, of course. And then this is a little extension. If you have c over x, well, it's c ln x, right? As though, remember, we said you can pass the c outside here, right? So you still have 1 over x there. So the integral of 1 over x is ln x, and then you multiply by c, and then you're plus k at the end. If it's a little more complicated, you have something like this. So you have 1 over a linear function. Remember, again, this has to be a linear function. If it's non-linear, this method will not work, right? So if you have 1 over a linear function, again, the answer is 1 over the derivative of that linear function, ln of the linear function, plus k. And we got some examples here for you. Right? First one, we applying this here, is this rule here. Second and third, we are making use of this formula. Right? Ln of 2x plus 5, or in front you put 1 over the derivative of 2x plus 5, which is 2. Right? 1 over 2 ln of 2x plus 5 plus k, don't forget k. Here, it's 3 over the derivative of the bottom there is minus 2, ln of 4 minus 2x, right? The modulus of it. Follow so far?
Yes, sir.
All right, so what I'll actually do, I'll stop there, because I just wanted to introduce you to integration this week. And we will continue with more, more complicated functions and so on. We're going to talk about integration by substitution, integration by parts, lots of other methods later on.